I'm substituting that Thomas Lecor, who cannot be with us today. So Thomas Lecor prepared this presentation, and I'll just help him. So to explore the first goal of the TGB1 was to work on real project analysis using the new Eurocode 7. One of the more important purpose was to make a comparison between the national practice and the new code. And another purpose was to evaluate the ease of use of the new code. And the last aim was to report bugs or comments on the draft of the Eurocode 7 second generation. TGB1 was divided into subgroups. Each subgroups were working on a section of part 3 of EC7. These subgroups was studying returning structures and anchors, and the people who composed the subgroup are quoted here: David Goals, Denis Igvik, Thomas Lecor, Claudio Popa, Valérie Wenham. Sorry for the pronunciation if they are here. There were 2 years of active works with 3 study cases studied. The first one was a K diaphragm with anchors. The second was a board pipe with anchors and struts, and the last one was diaphragm walls with struts, and this is the object of this presentation. The project is located here. It's north of Paris. It's an underground storm basin in Paris suburbs. There is one particularity to this project. It's located in a schoolyard, you can see here. The returning structure is insured by a diaphragm walls of 80 centimeters thick. For temporary works, the diaphragm is stabilized by struts, and during the exploitation phase, during life service, is stabilized by slabs. Some information about the project. The working seat is totally flat, so there is no problem of slope stability. The geotechnical investigation report was available and contained all relevant information regarding ground physical and mechanical properties. There was 2 kinds of investigations. There was an in-situ investigation with a pressurometer test and piezometers measures, and some laboratory tests with soil characterization and triaxial tests. One important problem issue is that the groundwater level is above the bottom of the excavation, so there will have some provision for execution, we'll see later. And it's a typical ground of Parisian sedimentary basin with a succession of embankments, moors, sand, and limestone. Regarding the basis of design, all design situations have been verified in construction phase, situation, service, and accidental. ULS and SLS analysis were verified regarding deformation and solicitation. There was a deformation criteria of about 35 millimeters, because there is no close surrounding buildings, so this criteria is not critical. First of all, the geotechnical category was defined according to the table 4.2 of the part 1. The class of consequences was evaluated as higher because it's in a schoolyard. It can be discussed, but it was CC3. The geotechnical complexity class was normal, so it was a geotechnical category 3 structures. And here you are reported here the consequence factor linked to the consequence class, and for us it was the higher consequence. So there is a consequence factor of KR of 1.1. There is some consequences on the design we will see later. Here you have the geotechnical model. So there was only one geotechnical model because there is no significant variation of ground properties on the wall structures. On the table here you have the different geotechnical units. From top to bottom you have embankments, moors, sand 1, limestone, and sand 2. It is a typical French project, so you have a pressure meter tests, so we have limit pressures, Maynard modulus and a rheological coefficient alpha. These coefficient, the parameters, Maynard modulus and rheological coefficient are used to calibrate the springs of the beam on springs model. Triaxial test permits to define the cohesion and friction angle. Here you see in the Mars you have very low friction angles like in limestone, so they are very weak layers. So usually those values are defined like a nominal value. This is based on the judgment of the engineer, and they are useful to determine the pressure at rest, active earth pressure coefficient and passive earth pressure coefficient. One of the most parameters for calculation of diaphragm walls is the value of the K tangent alpha, which is the ground structure interface coefficient. So usually in the French practice, the value of 2/3 is used both on the ground and excavation side to make calculation of the diaphragm walls. About representative water levels, so a slight adaptation of the Eurocode 7 is needed to apply totally the Eurocode 7 in France. So because the water pressure is factored by the same way as permanent action, there is no difference between permanent and variable part of water pressure. So the practice in France is to, over a time reference period, for example 50 years, is to associate a water level representative value to the different phases. For example, in the service phases, the quasi-permanent phases, the water level is associated to the water level that is reached 50% of time during the life period of 50 years. The characteristic water level is reached only one time during the period of 15 years, and the frequent is obtained 1% of time of the 15 years period. So for the geotechnical model, Ka and Kp are determined according to Annex D and using Capot, Kerizal, and APSI table. There was an approximation made, so the same Ka, Kp was considered for earth pressure and external load. Donc here you have the design model, you have the diaphragm wall, you have an head beam to control displacement at the head of the diaphragm, you have one level of temporary struts, you have the water level, different level for different situations. The water was temporarily drawn down inside the excavation site, and there was a limited flow allowed because of the restriction of the sewerage network. So deep wells were installed here, and the water level was controlled at the level of the tip of the diaphragm wall to avoid upward gradient, hydraulic gradient. So there was only horizontal hydraulic gradient. The analysis, the calculation are made with the correction coefficient method. This is the beams on springs models. This is really appreciated in France for this robustness. Here there was not very huge problem of verification of the displacement. If it was the case, we can use also with the beams on spring model, we can use also numerical models. The verification the verification carried out was the structural resistance of the diaphragm walls at SLS and ULS. It was with the combination of VC1 and RFA. The rotational resistance was verified with the combination of RFA and VC4. The basal heave was verified with MFA and VC3. The stress resistance was verified with RFA and VC1. And the bearing capacity was not studied in this case because it was not relevant. There is no loads on the diaphragm walls. Here you have all the results of the calculation. All calculations have been made with the consequence factor of Kf of 1.1. So in France, the practice is nowadays to do all the calculation with 1.0. The use of 1.1 has many consequences. There is no difference in the SLS solicitation, but there is an increase of USLS solicitation of about 10%. And there is an increase of the length of the diaphragm of about 10% too. Here you have, on the table, you have the different results for different phases. The critical phases is the construction phases, because in these construction phases you have not the slabs, so you cannot benefit of the resistance of the slabs. So the safety factor on passive earth resistance is the less important. It's 1.9. This is the reach for in French code. So the construction phase is verified. The SLS, the displacement were verified at the head of this. The head displacement of the diaphragm is less than 35 millimeters, and the maximum displacement on the diaphragm walls is also verified and less than 35 millimeters. Structural resistance of struts have been verified with a limitation of 90% of the yield resistance, the yield limit to the compressive over the compressive stress, and moreover there is a verification of the buckling situation. Due to the control of hydraulic gradient, there was no problem to verify the basal heave. Basal heave was verified with VC3. There is another possibility in France to verify the basal heave with RFA and VC4. This is less conservative than the verification with VC3. During works, there was a measure of the displacement of the diaphragm walls by inclinometers, and there was also a measure of efforts in the temporary struts with deformation gauges. In fact, during the works, we noticed that there was no deviation between the measurements and the calculation values, so there was no problem during works. There's provision to measure temporary sluts or displacement of the diaphragms are totally consistent with our current practice in France. And in conclusion, it was very interesting to participate to TGB1, and it was the opportunity to confront different practices from all over Europe. The pros of second generation of EC7 is that EC7 part is very complete and covers a wide panel for geotechnical structures. This is really the case for retaining structures or for pile foundation, but it's more difficult for other captors. It's easy to fit to national practices because of all vector tables are NDP. It offers a rich common ground to European engineers. On the other hand, compared to French practice, some factors linked to the consequent class can have a little an impact on the retaining structure design. We saw more or less 10%. It is the case for R and low consequence classes. But it results a possible increase of solicitation, minor increase. And there is an impact on design for temporary situation with construction steps. So in France, we usually reach 1.5 and not 1.9 of safety factor at temporary works. Okay, thank you.